So super informally, the limit of a function as its input approaches some value is just whatever value that function goes towards, right? For example, if our function is square root of x, we know that as x goes to 4, y goes to 2. And straight up, that's all a limit is. But let's drill down here and get something we can actually work with. So say we have a function f and some input c. We say that the limit of a function f as x approaches c is a value L if and only if y is near L whenever x is near c. So now we just need to explain what it means to be near something. So we'll just say that if x is near c, then x is within some tolerance level of c, and let that tolerance level be delta. Now to define y being near L, we do the same thing, except we define our tolerance level as epsilon. And so now we have all our pieces to make some formal definition where we say the limit of f of x as x approaches c is L if given any epsilon greater than 0, there exists some delta greater than 0, such that for all x not equal to c, if x is close to c, then y is close to L. The key idea here is that it's for any tolerance level of y. So effectively, no matter how small that epsilon is, we need to be able to find a delta to guarantee I'm within my y tolerance. And so here is the actual symbolic definition. And while that doesn't really provide any additional intuition, you should know it as that's what textbooks use, and you'll see that on tests and stuff. So let's say our epsilon was 0.5 in our root of x example, right? If you solve the tolerances from the last slide, you'll have to take delta equal to 1.75 since it's a tighter tolerance than 2.25. But you should note obviously that this doesn't really prove anything, right? Because according to our definition, we need to find a general delta for any epsilon, no matter how small, to guarantee that I'm within my y tolerance. So that's what we're going to do now. Note how I'm just restating the definition with this example's particular f, c, and L, and then I'm just playing with our required y tolerance to see what I can pick as my x tolerance. So here we just remove this absolute value and then move 2 to each side, and then we can square both sides and expand them. And now wait a minute here. We are subtracting and adding to 4, right? Which is what I need by the definition of absolute value. So we can do this where I surround my potential deltas with brackets, and then I just say, okay, if I pick any tolerance tighter than my smaller potential delta, I'm in the money. So now you should know this general pattern, right? We always start backwards. That is, while we want to start with my x tolerance and conclude that I'm within my y tolerance, we actually start by assuming that the absolute value of f of x minus L is less than epsilon, and then perform, some manipulations. And then we get an inequality of the form of the absolute value x minus c less than something, and we take that guy as our delta. And yeah, we're done.